Good morning, afternoon, or evening, dear esteemed participants of the ICLR2023 workshop on tackling climate change with machine learning. I am Racine and I lead the work related to artificial intelligence at ICLR2023 to support African Union member states to effectively implement the continental agendas in the agricultural sector. We see ourselves as mobilizers of African expertise, but also as providers of data and analytics to support African countries to effectively implement the Continental Agenda 2063 of the African Union. I've been asked to provide a keynote speech at this very important yet critical topic of tackling climate change with machine learning. I could not make it in person and benefit from all the important and insightful discussions you've been having. I'm currently in Morocco to attend a similar event, but with a different audience, the African Agriculture Adaptation AAA Initiative Annual Ministerial Meeting. African countries are particularly vulnerable to climate change due to a combination of factors such as limited access to resources and technology and dependence on agriculture as a primary source of livelihood. Climate change is causing a range of impacts in Africa, including more frequent and severe drought, floods, and other extreme weather events, as well as rising temperatures and sea levels. These changes are affecting food security, water availability, human health and biodiversity, and exacerbating existing social, economic, and political challenges. Moreover, many African countries lack the infrastructure and resources to adapt to these changes, making them more vulnerable to the impact of climate change. The effects of climate change in Africa are expected to intensify in the coming years, highlighting the urgent need for action to mitigate greenhouse gas emissions and build resilience in vulnerable communities. Data and analytics are critical tools in tackling climate change in Africa and globally, as they provide insights into the complex environmental systems that govern the continent and help us develop effective solutions to the challenges we face. By analyzing data from various sources such as satellite imagery, weather stations, and on-the-ground sensors, we can track changes in climate patterns, identify areas of vulnerability, and predict the impact of climate change on different sectors and communities. This information can be used to inform policy decisions, guide investments in sustainable infrastructure, and support climate adaptation and resilience efforts. Additionally, data and analytics can help us monitor progress towards climate goals, measure the effectiveness of interventions, and identify areas where additional action is needed. The most significant contribution of machine learning in all the sectors is its prediction capability, be it classification or regression type. It is helping us to make the invisible becomes visible, or at least blurry, to allow navigation in times of uncertainty such as the climate change and variabilities. Therefore, it has then a critical role to play into feeding the decision-making process, investment orientations, and monitoring progress by providing a most likely map of what would happen in the near future based on what we've been witnessing from the past. In the agricultural sector where I'm coming from, therefore, on the application side of machine learning, there are several examples where machine learning is being used in various ways to combat climate change. The first example I would like to provide here is in food crop production forecast. Machine learning algorithms can analyze various environmental data such as rainfall patterns, temperature, soil quality, and more to predict crop production and optimize crop management practices. For example, the Africa Agriculture Watch program at ICLR2023, AGWA in short, uses satellite remote sensing data and machine learning to predict food crop production in 47 African countries and for 9 crops. The model uses climatic and environmental data to provide its predictions. Therefore, any climate variability could be used to assess the impact in food crop production. The second example I would like to provide is in pest detection and management, where machine learning algorithms can be trained to detect pests and diseases in crops and provide recommendations for management and control. The International Center for Tropical Agriculture is using machine learning to analyze images of cassava leaves and detect signs of disease, which can help farmers act before it spreads. The third example is in climate-smart irrigation, where machine learning can be used to optimize irrigation schedules and reduce water usage in agriculture. For example, the South African Agricultural Research Council is using machine learning to develop an automated irrigation system that adjusts to watering schedules based on local weather data and soil moisture levels. And finally, in soil mapping and management, machine learning algorithms can analyze soil data and provide recommendations for soil management practices such as fertilization and tillage. The International Crops Research Institute for the Semi-Arid Tropics is using machine learning to analyze soil data and develop maps of soil nutrients, which can help farmers optimize their fertilizer use. But on the modeling side, several architectural and computational innovations are being proposed to improve the accuracy, energy cost, training time of machine learning models. For example, I can cite the recent advances in deep long horizon forecasting with time series dense encoder and in short tide developed by Google, which holds the promise of being 10 times faster in training compared to transformer-based baselines, while being more accurate on benchmarks. Such capabilities will allow us to soon adopt an exclusively data-driven approach for climate modeling, for example. Another example is in computer vision, where, for example, object detection is getting closer to the GPT-3 moment, with a hope of visual prompting to spread in the agricultural sector for crop and land features classification and change detection. The Meta's segment anything model, SAM, is a proof of that. Soon, we will be able to move from object detection to visual prompting, where only a few clicks will be needed to identify areas of a cropland suffering from water stress or what have you, tree counting, for example, in forestry, and also carbon stock, to only cite those. I couldn't end my contribution to this very important meeting without talking about the large language model, LLMs, that are on their way to become a game changer when it comes to making the information available to different audiences talking different languages. This could be used in disseminating information coming from climate services. As of today, it is safe to assert that the future of using machine learning to contribute solving climate-related issues looks bright. However, beyond the need to further work on adoption of machine learning in decision-making processes in Africa for quality, data availability and accessibility, and infrastructural investment, when it comes to solving climate-related issues, there is also the need to make sure that the outputs of any solution that we will be developing reach the most vulnerable communities, those who might first bear the cost of climate change in their livelihoods. In the agricultural sector, they are the farmers. And let me be clear, our livelihoods also depends on them. As we march towards and contribute to those great machine learning innovations to face our most pressing challenges, such as climate change, let us think about them as well. Ladies and gentlemen, this is a short contribution I wanted to share with you today as you delve into the many interesting discussions during the workshop. I wish you an insightful conference and fruitful deliberation that I'm sure will trigger new avenues of collaboration as well as very interesting topics that will bring us in the right path into using machine learning to tackle climate change related issues. Thank you so much.